All
Cool.
right, take it away, Dorian.
All right. Hey everyone, thanks for coming. This will be the first installment to our Catalyst Software Engineering course topic interview topic, and so today we'll be covering arrays and sliding windows. But so this is kind of the agenda for today. So we're doing the introduction right now, and then we'll kind of talk about what technical interviews look like because some of you might be new to this, so I want to kind of make that part clear. And then we'll go into our two example problems, and then I'll mention some extra problems you guys can look over, and just mention some closing remarks before we call it a day. So estimated time I think was roughly 45 minutes. So just keep that in mind, and if you guys have to leave throughout, feel free to do so. And yeah, so yeah, welcome again. This will be the first class, right? And we're recording this, so for those who are watching online, thanks for watching. And yeah, so first thing, we'll go right into it. What is a technical interview? So at the most basic level, technical interview is just solving a problem, right? So your interviewer will give you some sort of coding problem to solve, and you have to solve it and demonstrate your ability to the interviewer, right? And at first, I mean, it sounds simple, but the metrics for evaluation are actually a little bit more complicated, right? So what is the interviewer looking for? And I've broken it down into these two key points, right? One is they need to see that you're able to code, right? So this is kind of like the coding fluency check, right? Are you comfortable coding? Are you making a lot of mistakes? Are you, is your styling kind of off? Is your code hard to read? These are just things that come with practicing coding. And so this is kind of like the fluency, being able to code fluency test, right? And the second thing, which I'll argue is a lot more important, is the communication ability, right? So a software engineering job at the end of the day is teamwork, and you're working on a team. You guys are accomplishing a project, and you're constantly faced with various problems, and there are trade-offs, and you need to explain what you think is the right choice oftentimes. So the main reason why there are these technical interviews is to demonstrate that you can effectively communicate your ideas to your coworkers, and get them on board with whatever you're thinking, right? And so this second part is definitely a little bit less natural to us because oftentimes we'll think in our head and then just code up whatever we want. So this is a part that you guys really have to practice, and this is kind of the whole point of this course, right? Is we'll be addressing a lot of these techniques to solve these various types of problems, and then hopefully you guys can build enough foundation to be able to effectively communicate ideas, right? So we'll be going over how to break down some of these problems, and that'll be the focus of the course. So we're not gonna spend as much time on a solution, and we're really gonna spend a lot of time on crafting a solution, right? And how do you get from a problem to a solution, and how you can effectively demonstrate that, right? So throughout each session, we'll introduce some tips that you can use while interviewing, and so general interview tips, and also topic specific interview tips. And so I guess if you're pretty new to this, it still might feel a little bit confusing, but we'll postpone questions towards the end of the session, and then you guys can just ask away, and we can have a little bit more of a discussion. Right. So the topic for today is the sliding window, and this is a technique used to solve array problems. And the reason why it's effective is that arrays are static data structures, and they don't move, and they don't really change that much. So this kind of technique is pretty effective. You may have seen sliding windows in a CS201 APT, so they're back. Yeah, and so those who are not aware of what the sliding window technique is, or need some refresher, I have this little graphic here. So we have the two pointers, the red and the blue pointer, And basically, these two pointers define the window, if you will, right? The window of the array that we're looking at. And so depending on what your algorithm is, the pointers will move and your window will change, right? Hence sliding window. And depending on what window you're looking at, you might want to do different things, and you might want to terminate at different times, right? So is that sliding window concept clear to everyone? Cool. Alrighty. Yeah, so that's like the concept of the sliding window. It's fairly simple, but it's actually a really powerful technique that'll help us solve a lot of problems. So the first problem we'll look at is the longest substring without repeating characters. And so this is given a string, find the length of the longest substring without repeating characters. And if you think about like what a substring is, essentially, it turns out just to be like a window of a string, right? Where a string is just an array of characters. So anytime you see a substring, that's a good opportunity to maybe try a like sliding window technique on that problem, right? And now, so if you're looking at this problem and you might not be sure like how to go about solving this and where to start, right? And this will be true for various problems, ones that are more complicated than this one. So we'll go into our first interview tip, which will be start with a brute force solution, and then with the brute force solution, try to make some observations about the problem structure and see if that'll point you in the right direction, right? And the reason I recommend this is because oftentimes the reason why a brute force solution is bad is because it's not taking advantage of what makes an optimal solution optimal. So understanding the bad points of a brute force solution often translate into figuring out what the correct algorithm might be. And we'll see that today. I guess I'll make another side comment. Like if you're in an actual interview, I don't recommend coding a brute force solution unless you're really tight on time. But you can definitely talk about it at a high level, and that's kind of what we'll do today. Right. So to kind of revisit the problem, this is the substring problem, and so the brute force solution is not going to be too bad at figuring out, and it'll just be check every possible substring in the string and find the longest one that doesn't have repeating characters, right? And it's clear that this will be a brute force algorithm because we're literally checking every string no matter what, and there's very little logic to this. There are some ways you can improve the speed of this brute force solution, but in general, it's not going to be that great, right? And so looking at this brute force solution, one of the things that we notice quickly, and this will be our first observation, is that if we have a substring from index I to index j, which has a duplicate character, then the substring from index I to j+1 also has a duplicate character, right? And this is a pretty basic observation, but it's something that the brute force fails to recognize, right? That duplicate characters don't go anywhere in a given substring, right? So, and this will be true for like any string that contains that substring, right? And then like the other side of the coin, we can make like a pretty similar observation, which is that if a substring from index I to index j has a duplicate character, then the substring from index I+1 to j may not have a duplicate character, right? And basically what this is saying is that we could potentially remove the duplicate character if we shorten the substring, right? And with these two observations, we can actually kind of start pushing towards a solution. And I guess I'll also say, like, if you guys feel like you really want to solve the problem and you like have a good idea like halfway through, like you can totally mute me out and then try to code something up and then like come back and see how you did. So yeah, feel free to do that if you want. But yeah, so now we can kind of take some steps towards a solution, right? So the first point is kind of repeating the observation we just made, is that if we remove a character from a substring, we might remove the duplicate character if there is a duplicate character, right? And then we also, since we're kind of looking at these duplicate characters, we need some sort of method to tell if a given character is a duplicate character in a substring, right? So the first one will kind of point towards what our algorithm might look like, and then the second one is kind of is pointing towards a data structure, right? So like what kind of data structure we might want to use here. So I'll let you guys like think about the second point in the back of your mind, and we'll come back to that in like a couple slides. So yeah, so think about like what might be a good data structure for this, right? So before we go into a solution, we'll actually talk through a small example first, right? So so I've constructed this random string, just an array of characters, and let's say we're looking at B, C, D, E, right? So this substring here, and the characters I grayed out are ones that we won't be focusing on really. So like I said before, you know, we're able to kind of increase the substring length if we don't run into a duplicate character, right? So here we're able to include F into our substring because F is not a duplicate character, right? However, we'll reach C, right? And that is a duplicate character. So pushing the blue pointer along is no longer viable because we'll still have a duplicate character, right? And so the only other thing that we can do is we can push the red pointer along, right? Because we need to keep the integrity of the substring as much as we can, right? So we push the red pointer along, and C is still in the substring as a duplicate character, so we still can't push the blue pointer along anymore, right? So we move the red pointer along, and there we have a substring with no duplicate characters, right? And so this kind of basic example is like one that you definitely want to take advantage of when you can, because just kind of looking at this interpretation, we already have a decent sense of what the algorithm might look like, right? And so now to like kind of wrap towards the solution. So the first thing to note is that the empty string has no duplicate characters, right? So if you have no characters, there's no way to have two of a given character in your string. And the second thing, so if you've been thinking about like which data structure might be really helpful here, yeah, it turns out sets will be the most helpful data structure that we could use here. And that's because sets are very efficient at checking for duplicate entries. And so the way we want to use the set is the set will kind of maintain all the characters that are in the current window, right? So I'll like pause for a second if anyone wants to say anything. All right, cool. So yeah, so now we'll kind of walk through a pseudocode solution, and then we'll address like the code solution, and then go into like runtime and space analysis for that. Right. So for this pseudocode solution, someone asked a question. Yeah, we will be posting this video later on, so don't worry about that. Yeah, so this will be, we'll walk through the pseudocode solution now. And so the first thing we need to do is initialize the left and the right index and max length to 0, right? So the left index and the right index will act as our window, and then the max length we'll need to keep track of throughout our algorithm. Right. So the second step to do is kind of what we saw in that example, which is we can push the right index along until we reach a duplicate character. Right. And then once we've hit a duplicate character, the only thing we can do is to push the left index along until we remove the duplicate character, right? And this will be where the set comes in advantage because, you know, using constant time, like the set basically all has constant time operations, so we can remove, add, and check in constant time, which is really helpful. And then the next thing we'll do is just rinse and repeat, right? And throughout the process, we'll be keeping track of the max length we've seen so far. And then, of course, the last thing we need to do is just return the max length we've seen, right? That's like basically the pseudocode solution, and you know, feel free to like write up a code solution if you want. But yeah, so now we'll go into what your code might look like, right? So it doesn't have to look like this because this is how I coded it. So yours can look however much you want it to look like, right? So the first part will be is the initialization step, right? So we're initializing a bunch of things, right? And there's our set. And then we have the condition on the right pointer. And so we'll push the right pointer along down here whenever we can. But if we've hit a duplicate character, then we have to remove from the left side and then push the left pointer along as well, right? And then once we finish doing that, we're free to add the current character on the right to the set, and then update the max length as well. And so we don't need to have the max length in the second while loop because we're only decreasing the substring that we're looking at in the second while loop. And then increment the right pointer, right? And the last thing to do is return that max length. And yeah, there are definitely different ways to code this. You can use for loops if you want. You know, you've got a lot of options, but I think the hash set is pretty necessary here. And so now we'll go into like the runtime and the space complexity analysis. So the thing we'll note is that we only ever increment left and right at each iteration, right? And so we don't decrement either of them at any time, which means that each character at most will get seen twice, right? Once by the right pointer, and then the second time by the left pointer. So that's 2 n times. So our runtime will be O of n. And then I guess I'll throw up the information here. So this is the runtime part. And then the space is a little bit more interesting, right? So if, say, the string, it only contains unique characters, then we will end up putting the entire string into the hash set. So that'll be n space, right, where n is the size of the string. But there's also a chance that maybe the string is longer than the current alphabet we're using, right? So the alphabet size might be 26 if we're only working with lowercase letters, or it could be 256 if we're using ASCII encoding, right? So the size of the set will be the minimum of the length of the string and the alphabet size, right? And it's important to kind of call out the size of the alphabet here because, you know, like constraints are like different constraints are different, right? So I would avoid saying this is constant space because we don't know like what letters we're using or what alphabet we're in, right? But this alphabet size is something that you can take advantage of for like other problems. And it's also helpful for creating maps with strings. Yeah, so that'll pretty much wrap up the first example problem. And I guess I'll make like some statements first. So your interview probably won't look exactly like that, right? Because I've prepared like 15 slides to like walk you guys through a solution. So so your interview won't look like that. But the main takeaway is that you're conveying the thought process behind like going from the problem statement all the way to an actual solution, right? And it's important that like that process is more important than arriving at the solution, right? Like the journey is better than the destination, or something like that. Yeah, so that's that is the end of problem 1, and we'll go into problem 2. So,
Great, nice. I had a quick question.
Oh yeah, go for it.
Yeah, when I see a nested for loop, I'm so used to saying like O of n squared. Wait, why is this one O of n again?
Yeah, exactly. So yeah, that's a great question. And so yeah, you want to be careful because these aren't like for loops that just re-index at the very beginning, right? So the right pointer only increments once, right, in each iteration of the outer while loop. Mm-hmm. And then the left pointer only increments once at each iteration in the inner while loop, but it never increments out like in the outer while loop, right?
Gotcha. Mm-hmm.
We have the condition that the left is less than the right. So yeah, this is like the most important part, is that each character is seen at most twice, right? We can't, it's impossible to see a character more than twice, right?
Yeah. Gotcha. Thank you.
Yeah, good question. Yeah, so yeah, I guess we'll go into problem 2 then. So this is the container with the most water. So your input is an array of n positive integers, where each integer represents the height of the bar and the index represents the location. And you want to output the 2 bars, which together with the x-axis contains the most water. And yeah, so I guess I'll try to make this problem a little bit more interactive. So just keep that in mind. And now going back to the problem statement, the problem is kind of unclear a little bit, right? It's a little bit confusing. And if I saw this for the first time, I think I would be pretty confused, especially in an interview. So that will actually lead us into our, oh yeah, so I intentionally made it less clear because our next tip is to ask your interview clarifying questions, right? So if you're confused about the problem statement at all, definitely ask the interviewer, because you don't want to solve the problem, or I guess you want to solve the problem that they want you to solve, right? Not the problem they don't want you to solve. So make sure you're solving the correct problem. And a good way to do this is, you want to clarify things like the input types, and maybe like what are you returning exactly. And another good way to make sure that you've understood what the problem is asking for extra examples, right? So if they don't give you any examples, or they give you a really bad example, like I would definitely recommend asking for another example. Obviously, don't keep asking them for examples, because that'll waste time and they might not have that many prepared. So yeah, keep that in mind. And then you definitely want to be bringing up like edge cases throughout the process, and like kind of field their opinion on those. Right. So let's go back to the problem. So the input is an array, and so the output is the 2 bars, which together with the x-axis contains the most water, right? And so for this, the output is actually just going to be a single integer, and we'll kind of figure out what that integer is, right? But first we'll go through an example. So we have a bunch of indices at the top, and then we have the corresponding heights. And then this is like the graphical representation, right? And the 2 red bars and the blue water is the optimal solution for this problem, right? And so, yeah, so we'll see that we have index 1 here with height 8, and index 8 here with height 7. And so the width of the container will be 7, because 8 minus 1 is 7. And then the height of the container will be 7, because, I mean, if you put more water into the container, it'll just overflow, right? So the height is going to be 7. And so together, the area of the container is 49, right? 7 times 7. And just as a sanity check, we could maybe this solution might be better if we bring the right one here. and like doing some quick math, that's like 6 minus 1, 5, times the height, 8, 40. So, you know, it's not as good as the one we have here, right? And so with this kind of understanding, we could actually rephrase the problem into something a little bit more rigorous and something that will actually be more helpful, right? So we'll rephrase it as follows. So given n positive integers, x1 to xn, find the pair of indices I less than j that maximize the following equation: j minus I times the minimum between xj and xi, right? And this is just an area equation, right? Because we have the width here, j minus I, and then the height is the minimum between the two bars, right? So this is the formula for the area, right? And I guess I'll now ask you guys what might be a possible brute force solution to this problem. You like take some time to think about it. Feel free to call it out in the chat or unmute yourself.
Would it just be like a nested loop where you try all of them, all the different combinations,
Yeah,
all the pairs?
exactly.
Yeah.
Yep. Yeah, that's exactly. Yeah. Try every possible pair and then compute the best area, right? Yeah. So yeah, again, this is definitely the brute force solution because we're trying everything, every possible combination. Does anyone want to have a swing at the runtime for this?
Is this one n of squared of n squared?
Yeah, exactly.
Okay. All right.
Yeah, this will be an n squared solution. So this is actually something that's pretty decent to note, is that the brute force is n squared. So that's the time to beat, right? And so pretty much the only other times we have available to us are like either O of n or n log n maybe, right? But n squared is the time to beat. And so now we'll go into kind of like the first thing we noticed about this brute force solution, which is pretty general for all brute force solutions. And it's just that, you know, it doesn't acknowledge anything about the problem, right? It just tries every possible thing, which, you know, doesn't really help. Which means that we sort of need to make like some smarter choice about this, right? So with that, we'll like revisit the question, like this formulation of the question, and looking at the math, like does anyone kind of see anything that might be like worth stating, however simple or however complicated, preferably simpler, more simple?
Sorry, Dorian, I got nothing.
Oh, no worries, no worries. Yeah, so it's a little bit unclear, but just like a really straightforward idea is that since we're computing the area, right, we can look at some of the terms, and we'll see that j minus I is maximized when I is 0 and j is n minus 1, right? So this is the largest width we could possibly have, right? Because we're spanning the entire array. And we can like make the problem slightly simpler by just saying, okay, what if all the bars are the same height, right? Then the solution would be I equals 0 and j equals n minus 1, right? So that's going to be a helpful observation we can make, right? We do have some control over the width, right? And the height is like determined by the values in the array. So the second observation we need to make is that the brute force like tries all possible combinations, right? And so we need to try less than all possible combinations, right? Which means there are some combinations that are definitely not worth trying. Um, what those are, we don't really know yet. But we also know that I equals 0 and j equals n minus 1 could be the best solution on like the best solution that we have, right? So we definitely want to check I equals 0 and j minus 1, j equals n minus 1 at some point, right? Um, so now you might kind of be thinking back to the first problem we did, and maybe we can try like a similar algorithm, right? So does anyone like have any comments why that algorithm would work, would not work, or maybe what we can take away from that algorithm?
Um, I don't know. I was thinking maybe like do a reverse of what was you did in the first problem. Maybe like start bigger and like decrease your window, or like I don't know, like eliminate windows that like had it, makes it smaller.
Mm-hmm.
I don't know.
Yeah, that's a really good start actually. Yeah. So we kind of want to do so we definitely are doing some sort of window magic here. But so the issue with the previous algorithm was that there's like a huge shrinking step that happened where we just like shrunk until we got rid of the duplicate character, right? Um, and if we really want to make sure that we can check I equals 0 and j equals n minus 1, this solution might not be the one that we want to go with, right? And furthermore, it's also unclear how we should push those pointers along because, right, because there's no clear way, like as if there was a duplicate character in there that will tell us that this solution is definitely not optimal, right? So let's not worry too much because we'll like go back at the example and try to figure something out, right? So let's say we started with index I equals 0 and j equals 8, right? And now, so the answer to this one would be 8, right? Because 8 minus 0 is 8, and then the height is 1, right? The minimum height here is 1, between 1 and 7. And and this is definitely not the correct solution, right? Like I think almost any other ones will work, except for some. But I guess the question we need to ask is like from our perspective, how do we get from like 0, 8 to 1 and 8, right? And what makes I equals 1 and j equals 8 a better solution, right? And yeah, so what makes it better is that we've increased the height of the container, right, substantially, right? And we've increased the height more than we've decreased the width, right? So we've actually increased the total area of the container, right? Um, and that's like basically going to be like the breakthrough that we have in towards reaching like getting a lot closer to the algorithm, right? And so yeah, so to like summarize that, if we start with the left at 0 and the right at n minus 1, right? The only way we can improve this solution is if we can increase the height, right? If we can do better than the minimum of the left and the right, okay? And so with kind of this observation, we can think about like how we want to choose to like shrink the size of our window, right? Um, so actually, if does anyone have any ideas on like maybe like what choice we can make? yeah, so maybe if we take a step back, um, let's say we're at index 0 and 8, okay, and then we decided to shrink the right hand side, right? So we went from 0 to 8 to 0 to 7, right? Actually, this solution only got worse, right? We've decreased the width and we've done nothing to the height, right? And um, there's actually no way we could make this solution better. And there's actually no way we can maintain this solution because actually we might be able to, but in general, like we're going to do worse typically than we've done before, right? Like we have no guarantee that this will actually end up being better than the current solution. Actually, I think we have zero guarantee that we'll improve the solution by moving this bar down, right? That's because we've only decreased the width, and there's no way we can increase the height because this bar was the minimum, right? So yeah, so that'll, oh yeah.
So can we think about it then, like if left is like the limiting factor, it's useless in bringing the right closer in because left is already the limiting factor no matter how much, or is that an incorrect way to think about it?
Yeah, that's a good, I like that phrasing. Yeah, so here, like the height of the bar of height 1 is the limiting factor, right? And no matter what we do, right, that will always limit the height of the container, right? And so, you know, if there's a limit, something that is limiting us, you know, we should get rid of it, basically, right? Yeah, that's a really good point. Yeah, so that'll go into our pseudocode solution, right? And the first step, generally to any coding problem, of course, will be the initialization step. So we'll initialize our left and right, as well as the max area we've seen so far. So this part looks pretty similar to the previous problem. And then the second step will be, well, we've made it this far already, so what should we do? Well, we should compute the current area, right? Because this might be the correct area. So compute the current area and update the max if necessary, right? And then after we've done that, right, we need to move on. And so what we'll do is we'll shrink the window on the side with a smaller height, right? And this is exactly what Ayush was saying pretty much, right? We get rid of the limiting factor. And you know, there's no guarantee that our solution will get better, but there's a chance it could get better. Whereas if we shrunk the bar with a taller height, there's no way our solution could get better, right? So that's the kind of choice that we're making. And then, like before, we'll repeat steps 2 and 3 until our pointers collide, right? So we don't want to push the pointers past each other because then we'll be seeing containers that we've already seen before. And then we return the max area. And so I think this solution might be a little bit, if you like seen it straight up, it might be hard to wrap your head around. But I think with the way we've like kind of built up towards a solution, hopefully it's a little bit clear. And you could find like proofs for why this solution is correct, but hopefully like what we were saying earlier gives like you enough intuition to believe in this algorithm. Yeah, so the next slide we'll go into the actual code solution. So here we have the initialization step, and then we'll do another while loop, but this time we'll just be checking to make sure that the pointers don't collide. And then we'll compute the minimum height, which will just minimize between the two heights. And then we'll calculate the area. And then we'll max over this new area that we've calculated and the current max area. And then we'll do that step that we mentioned before, which is if the height on the left bar is smaller, then we shrink the left side. If the height on the right bar is smaller, then we shrink the right side. right? And then finally return the max area. And definitely this solution will be a little bit easier to analyze. So I just put it right there. We can never consider a bar more than twice, as in like we never increment into a bar more than once, sorry. So O of n, right? Eventually the pointers will collide and they've scanned like their respective parts of the array, right? And for the space, we've only used just some temporary variables. And so we have constant space here. And yeah, so I guess I made this like written out a little bit more lines of code than might be necessary. But I mean, there's definitely a simplification you can make here to like get rid of some temporary variables and just compute it straight up. But I also wanted all this code to fit on the slide, so that's why I made it a little bit longer. It is also a little bit more clear as well what's happening. Yeah, does anyone have any questions about this? Gotcha. Yeah, so Will asked an interesting question, right? So he said, I could imagine getting stuck when thinking that we're done once like the left and the right both decrease in height, like locally, right? That's actually an interesting question. So let's, all right. Yeah, so what's an example which kind of validates? So, okay, so say we had our pointer at 8 and our pointer at 6. If we were to decrease the height of the bar, right? So with the algorithm we currently have, we would decrease one of them, right? So let's say we decrease this one down. Then yeah, our solution won't get better. This one also comes down, our solution still doesn't get better, right? And that's just due to the fact that we've already seen the optimal solution, right? But we could also imagine a case where, like, let's say these two bars were extremely tall, right? Like a million, like they had a million height, right? Then it would totally beat this solution, right? This 49, right? So definitely we want to avoid making assumptions locally about what the array looks like at a global scale, right? Yeah, that's a good question though. And I do want to like reiterate the fact that like our entire algorithm was based off the fact that the max width is when the left is at 0 and the right is at n-1, right? And so if that's a max width, right, we're hoping that the bars there might also be, we were hoping that the bars might also be pretty tall. Like a narrow column, okay. Yeah, I think if you were bringing up an alternative solution that maybe did what you were saying before, Will, I think the interviewer would bring up this example of like a really, really tall bars and see how you handle that. But yeah, actually that's a good segue into my next interview tip, which is that you should always be in constant communication with your interviewer, right? So if you're trying to convey that you're good at communicating, then you should be communicating, right? So if, like, let's say you're really stuck on a problem, right? It's definitely way better to be honest and, ask the interviewer for some help than to just sit there like with your hands in your head, right? And I mean, but you also don't want to just, ask the interviewer, I'm stuck, can you help me out? Right? You need to like bring something to the table, right? So maybe you're stuck on like a particular constraint, right? Like, or you can like bring up a simplified version of the problem and, you can discuss, okay, it's easier to solve that one, but when we introduce when we like relax this constraint, suddenly it becomes a lot harder. Like, like, do you have any ideas on how I could proceed, right? And this is like totally reasonable thing to do, and something that I've like done multiple times in the past. So I definitely encourage this if you're stuck, right? You'll see harder problems, so it's better to be honest and not get discouraged and then trip up, right? Yeah. So with that, I want to hear some other problems you can try. So the first two are, I guess these are all like sliding window / array problems. So whenever you see array, the algorithm isn't always sliding window. So you also need to practice non-sliding window array questions. And I mean, some of these problems are pretty challenging. So I wouldn't like stare at it for 5 minutes and then go straight to a solution. Like I would spend some time thinking about the problem. Maybe like think about it for 15 minutes and then like close it and then look at it the next day. You might like get some inspiration, right? And also when you're doing the problems, it's a lot better to think out loud and like practice that communication piece, because that will be the most important part when you have your interview is that you're able to communicate well. And right, the only way to get better at it is by doing it. So yeah, those are like my tips for like this set of problems. And yeah, that about wraps up today's session. So thank you guys. And if you guys have any other questions, we can talk about like the problems that we've seen today, or just like interviewing in general.
I don't have any questions, but thank you, Dorian. It was really helpful.
Yeah, no problem. Actually, one other thing I wanted to mention was that like how you might be coding when you do an interview. So generally, you'll be coding in some sort of plain text editor that doesn't have like autocomplete features or like syntax warnings. So you want to practice in at least that, right? Because too much reliance on those features like might make it hard once you start coding. And then some companies will also do like pen and paper problems where you write the code in pen, or you write the code on a whiteboard. So it's also good to occasionally practice like handwriting code, just to make sure you have like some structure when you go into it, right? So yeah, that's a note I want to say about like what medium you might be doing an interview problem in.
Quick question.
Yeah.
I know CS201 is taught in Java and you use Java here. Is there, I don't know, just like what are your thoughts on like using a language like Python instead? Because like I know Python can be like simpler and like easier to write when you're writing quickly, but like Java has a lot of built-in things, like more formalized data structures that can like be of help. So like what are your thoughts on that?
Yeah, that's like definitely like that would be the pro and con to like Java and Python, right? And one thing I really like about Java is that you have to say the types of all the variables, right? And if you know what the type of every variable, then it's less likely that you will get tripped up on what a variable might be, right? Whereas in Python, you can just like just create variables whatever you want, and then it doesn't matter what they are, right? It's not clear what they are. So I think, but I mean, at the end of the day, right, it's about which language you're more comfortable in, right? So to the interviewer, they're just trying to see that you can code well, right? So if you're coding in Java or Python and you're doing it well, that's pretty much all like an interviewer wants to see. So I would like leave it up to you to decide which language is better for you. Having 201 in Java and like all those APTs in Java and like a bunch of leak code solutions are in Java, so that like might be a factor you want to consider.
Cool. Is there, I guess yeah, that Java makes more sense. Can you like shorten like a for loop Like that's just like the main thing I'm thinking about. Like if you're writing quickly, you're trying to get through a solution, like Python for loop would be way quicker. But like, do they expect you, does your interviewer expect you like write out the entire Java for loop and like formally like write everything out?
Yeah, I think so. I mean, I guess I feel like the difference between Java and Python, especially on these like algorithmic problems, might be like a couple lines of code. Yeah, I definitely like if you're writing bigger applications or bigger functions, like Python is like much shorter than Java will ever be. But I wouldn't worry too much about like typing speed for an interview. Generally, we can type pretty fast. Yeah, it might become an issue in like handwriting, but I guess we won't really be doing handwriting this season.
Yeah. Perfect. Thank you.
Yep. Yeah. Thanks everyone.